Hello friends, my name is Pawan. I am back again with another new topic in MRI machines, that is radio frequency wave in MRI. As you can see in this slide, two sinusoidal waves propagating simultaneously with a 90-degree shift, that is called radio frequency wave. This is an electromagnetic wave. Waves of electrical and magnetic energy moving together is called RF wave. Okay, this collectively you can say it as a radio frequency wave, RF energy. Okay, so in our MRI machines, normally the alarmer frequency is actually 63.66 megahertz. Basically, you will see this, if you will see this frequency spectrum, that the frequency will be lying somewhere here, that is here. This is our MR frequency. We use MRI machine in this range, that is very high frequency. Okay, high frequency means shorter wavelength. Okay, means wavelength. If the wavelength is short, the frequency will be high. Okay, so this is our frequencies, that radio frequency radiation spectrum. I just wanted to show you where exactly which frequency we are using in our MRI machines. So this is an example of an overall MRI machine. You can see here, this outer one is your magnet. This is how a MRI machine looks like. This blue color you can see is a gradient coil. Okay, and the inner one, this inner one you can see, this one is your body coil, or you can say transmit coil, TX coil. Some companies refer it as a TX coil. This coil is transmitting RF to the patient body. Okay, this is called RF transmitting coil. Okay, so this diagram is clear, and this is your electronic cabinet, all the electronic computer, server, post-processing things, so many items are involved in that, just to show you. And this is a patient table, electronically controlled. So clear. So this one is magnet, outer one, this blue color ring is a gradient coil, inner one is your body coil. Okay, another diagram, the cross-sectional view of MRI machine. You can see here from this side, you can see the outer part is a magnet. Okay, you can see here, see this one is your magnet, another is your shim coil. Shim coil, actually what is shim coils? Shim coils are here, first you see the gradient coil, this is a gradient coil, and this is your transmit coil or RF coil. So what is shim coil? Shim coils are actually embedded inside the gradient coil. Okay, so suppose this is your MRI magnet, inside MRI bore there will be another coil, this is called gradient coil. Inside that there will be one more coil, that is called, this one is your RF transmit coil. Okay, and this one is your RF transmit coil, this one is your GC gradient coil, and this outer one is your magnet. So what is shim coil? Shim coils are actually those coils that makes B0 field homogeneous. Okay, so in this diagram, if I show now, B0 is like this. So to make the B0 field homogeneous, we use shim coils. Shimming, we use the shimming. Shimming is actually of two types, active shimming and passive shimming. Okay, so passive shimming means we are loading some iron plates, passive shim. Okay, and active shim, two types of shimmings. Passive means loading the iron plates inside the magnet. Active shim means we send the current for homogeneity, B0 homogeneity, that we'll see in some later steps. So this is the another diagram. As you know, this is your magnet, this is your gradient coil. You can see here, this is your magnet, this is your gradient coil. And so we are mainly, actually we are interested in this part. Actually this is our part, RF coil. In this class we are just discussing about RF systems and RF electronics. So we will see the next one. See about RF. You can see I have made a basic block diagram of RF oscillators. You can see here RF oscillator. We are using RF oscillator. It is actually a frequency controlled and frequency range controller device, oscillator. It creates a fixed frequency signal, an alternating signal. We are giving this signal here to an amplifier. Basically amplifiers are like an operational amplifiers, and this is a feedback circuit here. whatever input we are giving, we are getting that same output here. So we are giving the changing signals, alternating signals like that. Okay, and this is the amplifying that signal, and after calibration and attenuation we are getting the signals here. Okay, and whatever signal we are getting here, alternating signal, that we are giving to our amplifier. See, this is the amplifier, as we have explained now. Whatever output we are getting as in the form of electromagnetic wave, in the form of alternating signal, whatever alternating signals we are giving, okay, to this, we are giving this signal to the amplifier, and that amplifier is feeding those signals. Normally in most of the companies are using a 0 and 90 splitter. Okay, they split this incoming RF in between 0 and 90 plane, and this is your body coil. Body coil is what? Actually it is the electromagnet. This is a magnet. Okay, we are giving a current, so current direction changes. First the current will go like this, and second the current will go like this. So one time the magnetic field induced by the current will be in this direction, another time will be in this direction. So the changing magnetic, understood my point? The changing magnetic field, what is the RF? The field that is changing means this direction and this direction. So the field is changing. So this is your transmit antenna. All the RF signals are being transmitted to the patient body by this RF coil only. Understood? We are generating as alternating signal, we are amplifying that signal, we are splitting that signal between 0 and 90, and we are transmitting to the patient body. And this is a kind of dummy. Whatever reflecting RF reflection we are getting, all these reflections are going to the dummy. Okay, so this is another good photograph showing the body coil. This is the transmit coil, this one is the RF coil. From this coil we are transmitting the RF to the patient body. Okay, so we are giving RF signals to this coil, and this coil is behaving like a RF antenna, and it will transmit the signal to the body. These are all, you can see in the diagram, these are all local coils. This is the head coil, this is your flexible coil, this is your knee coil, this is your knee coil, this is your abdominal coil, this is your head coil. These are all called receive coils. Okay, and this is your TX coil. So from the TX coil we transmit RF to the body, and from the local coil we receive RF. Okay, so now we will go little in hydrogen physics. Okay, this is your hydrogen atom. As you can see in this diagram, hydrogen, if you remove this electron, only that hydrogen atom will behave as a proton. So if you keep this proton in a magnetic field B, see in this diagram you can see this is a main magnetic field because of the magnet M0. Okay, so if you keep this magnetic field active, so your hydrogen, actually you can see your hydrogen is normally spinning in its own axis, you can see, and also there is a precision like a top, you see here. This one is precessing with a Larmor frequency of 63.66 megahertz, 63 megahertz. Okay, two motions. This atom is spinning in its own axis, and also it is precessing. So two motions are there. So conclusion is, when there is a magnetic field, okay, and if we put a hydrogen atom inside that magnetic field, it starts precessing. Okay, and also spin in its own axis. Okay, we'll see next part. You can see in this diagram that in this diagram you can see this diagram that this is the patient lying, and this is your main magnetic field in this direction. Okay, and all the hydrogen atoms are pointing in this direction, so all these atoms are aligned. Okay, and these atoms are not stationary. These atoms, now in this picture you can see they are all stationary, but it is not stationary, it is precessing, it is moving, and this is your main magnetic field. Okay, so these all atoms, this one, and this atom, all these atoms are polarized. You might have listened in the news channels that all the people are getting polarized against that party. Okay, so people are getting polarized. So polarization means everyone start thinking in the same direction, everyone start moving in the same direction. So these hydrogen atoms are polarized and they are aligned in one direction, means they are doing a precision. You can see here in this diagram, when there is no magnetic field, the hydrogen is like this, is doing a spin only. And if the magnetic field is active, means there is a main magnetic field, then it will start, this hydrogen atom will precess, okay, like a top, means this will be here, after some time it will go here, 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 like this it will precess. Okay, here you can see no magnetic field, here magnetic field is active and all these atoms are aligned in one direction. And this is a diagram to show you that these atoms are aligned and precessing. These atoms are precessing. See, uniform magnetic field is there and all atoms are moving in same direction. You can see here that all the atoms are moving in the same direction. The precession speed is same here. Okay, you can see in this diagram is a very good animation. You can see this is a magnetic field. If I draw this, okay, this is your hydrogen atom and this is your main magnetic field. Okay, you can see it as a B0. Okay, and this person is RF transmitter, electromagnetic wave transmitter. So this guy is transmitting RF to this hydrogen atom and this hydrogen atom is flipping. Now is from this direction, this atom starts flipping, okay, like this 90-degree flip, furthermore down, it's going furthermore down and precess, and then again it starts coming back like this, it's going back and in the home position. Okay, understood? You can see in this animation we applied the RF, okay, and this atom, this vector starts and flipped here, again going back, but the movement is a helix movement, it's a spiral movement, so it's little tricky to understand, but this animation is making clear. Here you can see another good example to explain you. We are supplying RF. This is your hydrogen atom. Okay, you can see here, this is your hydrogen atom. This is your, suppose, on Z axis, this is your X plane and this is your, suppose, Y plane. Okay, so you can see here that this vector is this hydrogen atom, this is the hydrogen atom. Okay, if we give RF, it starts getting and excited, and in the final excitation it goes here. Okay, so this is the transverse plane, this circle is the transverse plane. See, this circle is like a transverse plane, so it starts moving. See the helical path, the spiral path that this atom is taking. Okay, so this is the excitation of hydrogen atom. We are giving the RF and this atom is getting excited from 0 to 90, and this is the relaxation. Okay, so now the RF is off, no RF is supplied, we removed the RF. So what is happening from, see, this is my plane, so from this plane it's going and my atom is going up. So to explain this thing to you, okay, I am making one vector here. This is the hydrogen atom. Okay, so we gave RF. Okay, we gave RF. This is the main magnetic field B0. So my hydrogen atom, this is the hydrogen atom, after getting the RF it got flipped, suppose some theta degree. Okay, this is the hydrogen got flipped. After getting the RF, this hydrogen atom came here, so this will be H cos theta and this will be H sin theta. Okay, after some time this vector will go here, again here, 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 so maximum, this vector will be maximum, and when this relaxation will take place, this will go back. Okay, again when this movement will happen, this vector will reduce. Okay, this vector will reduce. Okay, so from here to here the time taken is called T2. Here you can see this animation, you see this is the vector is reducing. Okay, horizontal vector is reducing here, and longitudinal vector will increase because that vector will come to its own position. Okay, so you see this diagram, and this vector from here to here, the time it takes to achieve this full longitudinal position is called T1, and this one is called T2. And the very popular graph is this. The main graph for this is this, and the main graph for T2 is this: transverse relaxation time and longitudinal relaxation time. Here you see the same diagram again. Here you can see, just pay attention to this black shadow. Okay, this is your z-axis main magnetic field. Okay, just see two shadows. Your yellow vector, you see this is the yellow vector I am drawing. You can see one shadow. Okay, and one shadow here. Okay, so this is decreasing. Okay, from here to here this is decreasing, and this one is increasing. Okay, so to understand the motion of this vector, okay, this is flipped, this is the hydrogen vector. To understand the motion, how it is from here to here, this vector is moving from here to here, and when the RF is removed, this is going back. So it takes a spiral path. For simplicity we understand, so this vector reduces. Okay, so the time taken is called T2, and this vector vertical component is increasing. So the time taken here is called T1, longitudinal relaxation time, and this is transverse relaxation time. This is a very popular graph you can see here. This is T2 and this is T1, longitudinal relaxation time, transverse relaxation time. Now you see, let us take an example of a magnet. See, this is a magnet. Suppose this is a magnet. Okay, up, and you can see here there is a gradient field applied. This is a magnetic gradient field, you can see here. So inside the magnet bore, if we apply a gradient field, each and every place, has a particular, see this one I am drawing, this is a main B0. After gradient the field is different. Each and every point there will be a different field strength, and definitely each and every point has a different frequency. So we are interested, suppose in this diagram we are interested in this slice. Okay, we want to do some scanning here, this slice of the patient body. So we want to select. How we do the slice selection, how we are going to select it? So gradient is applied, and we know what is the frequency of this point, and we know what is the frequency of this point, because there is a field gradient. So inside the magnet, each and every point will be different frequency. This point has a different frequency, here is different, here is different, and different. So this one is F1 frequency and this one is F2 frequency. If we know the frequency band, okay, so according to that frequency, same frequency band, whatever frequency band is here between this point and this point, same frequency band RF we will apply from this frequency band to this frequency band. Means whatever is the limit, like from, suppose you can say that from 61 Hertz to 61.5, all the frequencies are in between here. This is called frequency band. So same frequency band RF we will apply, and what will happen? This RF the body coil. Here is the body coil. So by the body coil, the RF will be applied to the patient body. So this entire body hydrogen atoms, all the hydrogen atoms inside the body will not excite. Only the hydrogen atoms, those are in the same frequency band. Means if we are applying the same frequency of these hydrogen precision frequencies, resonance will take place. Whatever frequency these hydrogen atoms are having in this slice, whatever frequency of the hydrogen atoms are there, we are giving the same frequency RF. Okay, and because the frequency is matching, so resonance will take place and hydrogen will excite. Okay, and when we remove this RF, energy will get released from here. So we receive the energy and we use receive coil to receive the energy. Like here you can see RF pulse we are applying and slice selection gradient is applied. See, this is the slice selection gradient and we have applied RF. Each and every point has a different frequency. Okay, you can see in this diagram each and every point has a different frequency, and because of that, whatever slice we want to examine, suppose this slice we want to examine, so we know the frequency of this part and we know the frequency of this point and this point. So we know the frequency range. According to that frequency range, we will apply the RF. Okay, so this RF frequency range will be the same frequency, that frequency we want to excite. Okay, so these atoms we want to excite, we want to create a resonance. So whatever precision frequency these hydrogen atoms are having, same frequency we will use in the RF and we will give the same frequency. Then what will happen? Resonance will happen and hydrogen atom will get excited, and once the RF is removed, energy gets released. All energy from this slice will get released. So we capture this energy in a receive coil and we start doing the imaging. And this is a very universal diagram. You can see here we are using the RF is applied, here RF is applied, slice selection gradient is applied, patient is lying, suppose this is the patient, this is a MRI machine, so slice selection gradient is applied, that body is divided into different slices. Okay, slice selection gradient is applied, then phase encoding gradient will be applied. Like depending on the matrix, if 512 is to 512 matrix is there, then 512 steps of phase encoding gradient will be running. Like that gradient sound, abnormal sound comes, that is phase encoding steps, and then frequency encoding step will take place, that is called readout. So we will capture the data here and this will be your MR echo. Clear? And this is the voxel diagram I tried to make here. You can see this is one voxel diagram. If you see this, there are different slices. Okay, like if you want to see in this voxel, the slice selection will be in this direction. This is slice selection. So if slice selection gradient is applied, so slice selection will be in this direction, and this direction is your frequency encoding direction. Okay, and your phase encoding direction will be this one. Like this, all three, X, Y and Z. One is slice selection gradient, another one is frequency encoding gradient, and third one is phase encoding gradient. Okay, I have made a separate video on different gradients: slice selection gradient, frequency encoding gradient and phase encoding gradient. If you want to go through that, you can go and see my previous videos. And this is general images I included here: T1, T2 and PD. Short TR, short TE is called T1, long TR, long TE is T2, and PD contrast is like long TR and short TE. Okay, if you want to see that, I think I skipped. So T1 and T2 I already explained you. T1 is longitudinal relaxation time, this one is transverse relaxation time, and TR means 90-degree pulse you have given. Okay, slice selection gradient is applied, phase encoding gradient will work, frequency encoding will read your data, and then you will get, after TE time, you will get the echo. This is your MR echo. So TE means the time when you get MR echo is the TE, time of echo. Now another RF you are applying here, again same thing will repeat. So TR means time of repetition and TE means time of echo. So short TR, short TE is T1, long TR and long TE is T2, and long TR and short TE is PD. So this is all about RF excitation, relaxation, TRTE, and how we are using the RF in slice selection. Hope these points are clear to all of you, and if you like my videos, please subscribe my channel for all upcoming new videos. Thank you.